Hello everyone, welcome back to another video of NL Maths. Today we'll be looking at Euler's identity. E to the ix equals cosine x plus I times sine of x. So this is weird really. How does an exponentiating function which goes whoop equal to a periodic one like a cosine and sine? Perhaps I is very special itself. So we are going to be, actually I should give you a review. I is the root of -1. And we'll be looking at the squares and the cubes and the quadruple ones as well. So I squared will be -1 because you're cancelling the square root. Then I cubed is going to be -I. And I to the 4 equals to, I equals 1, because I squared, I4, they should be opposite because it's -I. So I'll write this down in a box. Okay, so those are our I identities. And now we'll be looking at the MacLauren series. We'll be expanding each term out to see if they truly match with each other. So I'll write down MacLauren series. And this is equal to the sum from n equals 0 to infinity of fn at 0 over n factorial times x to the n. So this n just means the derivative, the nth derivative of it. And now this is quite similar to Taylor's series, which means that this is supposed to be at a and this is x minus a. So what a Taylor series does, for a quick side note, I'll just turn the sheet around because I don't need this part, is that, let's say I have here sine pseudo, then cosine, and then we'll evaluate the point with no derivative here, then we'll evaluate the parabola, then we'll continue on by the cube like this, then the fourth, etc., and it will slowly mark out the whole entire graph for analytic functions, which of course for future knowledge, analytic functions satisfy Laplace's equation. So we have the MacLauren series, it expands it at 0. So we'll be looking at e to ix, expanding that, cosine of x, and I sine of x. So for e to the ix, this is going to be equal to, and actually I'm going to write it from step 1, and so we'll have f of 0, because we don't have the derivative, over, and this is the 0th term, so 0 factorial, which is 1, but we'll write that later, and x to the 0, which is also 1. And then we plus, and I'm going to do all of these to the 5th term actually, plus f prime of 0 over 1 factorial x, and then you can see a pattern really, f prime prime of 0 over 2 factorial x squared plus f triple prime 0 over 3 factorial x cubed plus f prime. Oh, I should start writing it in this form really, of 0 over 4 factorial x to the 4. We have 5 terms here. Actually, I should have one more. Can you see this? I'll write it here. Plus f to the 5th derivative at 0 over 5 factorial x to the 5. So we'll be looking at each individual term and we'll be writing that out. And then plus dot dot dot, of course. And this f of 0 is e to the ix at 0. I times 0 is, of course, 0. And anything to the power of 0 is 1. So this whole term is equal to 1. Then the next term, we'll have f prime of 0 over 1 factorial. The derivative of e to the ix, actually, I'll write another side note here. D by dx, e to a constant, e to maybe lambda x, would always equal to lambda e to the lambda x. So continuing on, if we have this, the second derivative, this is going to be this, the derivative of this. So which means that we'll take another lambda, and so e to the lambda x. And this is going to be lambda squared e to the lambda x. So as you can see, as it goes on to dn by dxn of e to the lambda x, it's going to be lambda n times e to the lambda x. And you can try doing some more, proving to yourself that this is the truth. So back to this, 1 plus f prime of 0 is going to be I times e to the ix. So I'm going to write that fully. And over 1 factorial, that's 1 times x. So that's the second term of the series. Plus f prime prime, so that's I squared. And I think you can see the pattern here, so I'm going to quicken this part up. Of course, you can try this by yourself, convince yourself as well. E to the ix over 5 factorial x to the 5th. Now, what you're going to see as well is that I did an extra step, because e to the ix, if at 0, of course, it's like the one argument. I times 0 is 0, and anything to that is 1. So technically, all of these terms go to 1. So I'm going to write this a little bit nicer. And also, as well as that, from our previous identities with I, we can see that I squared is actually a real number. So I'm going to write that out as well. And I cubed is, of course, negative I. So negative I over 3 factorial x cubed plus I to the 4 is 1 over 4 factorial x to the 4. And I to the 5 is, of course, I again, because it's a loop that goes on. Now, if you look here, we have some terms that belong with the reals, so they're all real value terms, and some terms that belong with I, so they're complex value terms. So we're going to split this up into the form, so a complex number usually is in the form x plus iy, so that's what we're going to do really. And we're going to have 1 minus 1/2 x squared, and then we have plus 1 over 4x to the 4, and then that's going to be the first term. And then we have plus I, and then actually, since all of them have I only, I'm going to take it out. Plus I times, so the first term is I times x, and the second term is minus 1 over 3 factorial x cubed, because this is a negative sign. And then finally is plus 1 over 5 factorial to the 5. So this is what e looks like if you expand it using the MacLauren series. And what we'll see here, it looks like it's in the form of this. Well, all complex numbers do. So what we're going to do, we're going to expand cosine of x and I sine of x. I mean, just sine of x. And then we're going to see what that looks like in terms of this, see if it matches. And that's going to be the end of this mini lecture. Okay, a bit of pen markings on it. So we can expand cosine of x first. And what is this going to equal? Well, first, actually, I think it's good to have a reminder of the derivatives of cosine and sine. Actually, I shouldn't write it there. I'll write it here. So if you derivate sine, then this is going to be cosine. You do that again, that's negative sine of x, then negative cosine of x. So all of these, you're applying the d by dx operator. And that's what it looks like. So cosine of x, the first one is cosine of x at 0 over 0 factorial times x to the 0, which is all 1. Then we minus, because we're deriving it once, and that'll be minus sine at 0 over 1 factorial times x. Then this is going to be minus cosine at 0, because this is the second derivative, over 2 factorial x squared. And we're going to do a third term, but I just want to point out this is f of 0. This one is f prime of 0. This one, just the cosine of 0, is f prime of 0. And I'm not going to write that out again. So the prime of negative cosine of 0 is sine, so this is plus sine of 0 at 3 factorial x cubed. And what you see is cosine of 0 equals 1. But sine of 0 equals 0. And what we're going to see here, actually, I want to expand it to one more term because our Euler's one use one more term as well. So plus, and then the derivative of sine is cosine. So that'd be cosine of 0 over 4 factorial x to the 4. And then this is going to be 1 over plus 1 over 4 factorial x to the 4. So we can see that some terms cancel out. This one's gone. This one gone because it's a 0, which means that this would be 1 minus 1/2 2 factorial, which is just 2x squared, plus 1 over 4 factorial x 4. And you see that there seems to be a pattern because cosine of 0 is always going to be 1 and sine of 0 is always going to disappear. So it seems like it's going to go on in even. It's an even function as well. So if I were to predict how this is going to continue, it's going to be maybe minus 1 over 6x to the 6 plus 1 over 8 factorial x to the 8. And that's cosine of x. So now let's look at sine of x. And then f of 0, sine of 0 is just sine of 0 over 0 factorial times x to 0. And then the derivative of sine is cosine over 1 factorial times x to the 1. And that's going to be negative sine now. Over 2 factorial x squared. And then that the derivative of sine 0 is cosine, so negative cosine. Okay, and then the final term of our MacLauren series is going to be the derivative of negative cosine, which is sine. Yep, okay. And then for factorial x to the 4. So that's nice. We can see that sine of 0 is equal to 0 from previous. So these terms with sine of 0 always disappear. So then, oh my gosh, I'm so sorry. This is supposed to be 0. So then now we have cosine of 0 times x minus cosine of 0 over 3 factorial x cubed. And we know that cosine of 0 equals 1. So that'll be equal to x minus 1 over 3 factorial x cubed. So this is cosine x. And we can see that it's only in odd ones because, of course, it's the opposite of the cosine. So sine is always in odd, so it's an odd function. And if I were to guess, maybe it's going to be plus 1 over 5 factorial x to the 5th. And we can actually try that out. This isn't really part, but it's just an extra. So the derivative of sine, this is the fourth term, the derivative of sine is cosine. So, of course, as predicted, it is going to be a valued function over 5 factorial, and this is positive, and, of course, x to the 5th. So this is what we predicted, which equals to 1 over 5 factorial x to the 5th. This is what we predicted, and the next term is going to be a sine term, so that's going to disappear, and it's only going to be odd functions. So we've got this one and this one as the MacLauren series for sine and cosine. And if you look at that, if we look at our previous one, 1 minus 1 over 2 factorial x squared plus 1 over 4x to the fourth. This is equal to cosine. So I can write that. Cosine of x plus I times, and if you look at that actually, oh, I forgot to expand it to the fifth, x minus 1 over 3 factorial x cubed plus 1 over 5 factorial times x to the 5, that is equal to sine of x according to the MacLauren series. So there you have it. We have proved Euler's formula to be equal to e to the ix equals cosine of x plus I sine of x using the MacLauren series. We looked at the expansion of e here. Then we looked at the expansion of cosine x, sine of x, and we saw how it matched with cosine x plus I sine of x in the expansion of e to the ix. So I hope you enjoyed this video. It was quite a long one, and I hope you learned something. Thank you, and please subscribe.